Welcome. So, you've done those lessons. We've got to a stage where we know how to observe stars. We know how far away they are, roughly. We're kind of thinking of them all the same, a little bit on the fact they've got some different colours. Now, when you get to this part of the qualification, then we really get into detail of what's out there. So we've been dealing with how we work out these things with telescopes and different bits and pieces. Now we're going to deal with what we've actually discovered using these telescopes. And we've discovered a lot. And the detail has got so much more in the last, 30 or 40 years with the launching of space telescopes, and also the detail in which we can look at in terms of spectra. And any astrophysicist worth his salt deals with spectrum. Spectra of stars will tell you everything about the chemistry of what's going on inside inside the atmosphere, on the surface, and surrounding as well, and some of the weird and wonderful objects that are around. Now, this lesson I'm going to attempt to do nearly everything we've got on this part specification, but you're going to be doing a lot of learning. This top table here, the OBAFGKM, all these, you have to remember these things. I'm going to give you some techniques for how to remember it. It's just hard work, I'm afraid. You have to write these down and do the memory games, everything to be able to do it. This little line here hides quite a large conceptual part of the course, which is really quite hidden there. Hydrogen Balmer resorption lines is quite hard, so I'm going to spend more time on this than I am on this bit. And then we're going to look at the Hertzsprung-Russell diagram, which is a way in which you could represent all these stars. And then we're going to move on to what the sun looks like on that diagram. But a lot of it centers around the fact that there are different types of stars that have different colors, different temperatures, and different types of spectra. And so if you've got your notes, get the title down, classification of stars by color and brightness. Those are your 4 lesson objectives to be able to apply spectral classification, which is what we're dealing with. That's what that table was, to be able to construct a Hertzsprung-Russell diagram and to compare how stars would appear using spectral information, and then talking about hydrogen Balmer resorption lines. I'll explain everything that I've said, by the way, including what a spectrum is and also what hydrogen Balmer. What's hydrogen? What? Hey, I'm not a chemist, I can hear you saying, but actually, this is all about astrochemistry. Working out what's going on in a star that is light years away, hundreds of millions of light years away, just by looking at the light that comes off it. That's why I love astrophysics, because you can do a little detective story and work out what's going on and never having to visit it. So, okay, this you have to remember. You have to remember the spectral class, which is essentially a letter which is assigned to a color of a star, which then refers to a temperature range, and also the absorption lines that are in there. And I'll explain what those are in a second. So, just to get these in order, and you have to remember them in order. O is the bluest, that's the hottest type of star. I know it seems strange that blue is hot. It's not like the taps in your bathroom at home. It's blue is the hottest, white hot. And it goes way hotter, it goes to blue in fact. And these stars are 25 to 50,000 Kelvin. The hottest, not quite the hottest stars, but they're very hot stars. And then you have things called absorption lines. These are dark lines in all of the light that is coming from the star spectrum. When we learn about Wien's displacement law, we'll learn about the different spectra that comes out of stars. But just for now, take my word for it, there are dark lines that appear in the wavelength spectrum. So you know what a spectrum is, it's intensity versus wavelength. It shows you the different outputs of a star at different wavelengths. So this particular star, its peak output is in the blue. It's a blue star. You look at it, it looks blue. Why? Because most of the light coming out of it is blue. Yeah, some bits come out in different places. And the peak of that spectrum is blue because it is this temperature, and colour and temperature are linked. Now, as it goes blue, 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 white, white, yellow, white, orange, red, you might think, hang on, top two are blue. Yeah, because they're blue. That's why we use the temperature, because temperature is a much better range. However, OB is the next one, which is 11,000, 25,000. A, which is 7,500 to 11,000, and so on and so forth. First little memory game. How do I remember the order of these? At the bottom of here, there is 6 suggestions. Now, for me, the only one that ever existed when I was at university was this top one, because we lived in a land of sexism. But actually, there is a opposite sexism one, which is down this one, which I think is great. So whichever one you want to do and to remember, it doesn't matter what they are, it doesn't matter who you are, just remember one of these. Personally, it's "Oh, be a fine girl, kiss me," because I'm a boy and I like girls. Now, if you're not a boy, and oh, hang on, if you like girls, for instance, only boys accepting feminism gets kissed meaningfully. So therefore, you can use that one instead. And you only need to know down to M. You don't need to go, this is why this is right now. Smack was actually the one that I remembered. And that was the way in which you could get out of the sexism by the fact that if you say that, then you get smacked in the face, which is fair enough. So it was "Oh, be a fine girl, kiss me right now, smack." Or you can go for this one down here. Don't mind, "Oh, be a fine girl, kiss me" is the one that I remember. There you go. So, and there's one. Now, how do I remember these temperatures? This is how I do it. Remember the top, remember the bottom, and remember the middle, and then you've got your benchmarks. Now, in between, you can notice that the gaps are not the same. They're not the same at all. And then you end up with ones that are a little bit different. So, here we go. Remember, 25 grams to 50 grams at the top, 3.5 grams at the bottom. The middle is where F is, which is 6,000 to 7,500. Get them, and then the others, because you've only got between 6,000 and 3,500 to cram in. So the one beneath that is just a 1,000 range. The one below that is a bit more, 1,500. You've only got a little bit to be able to get in there. The next ones, of course, are 7.5 to this. Now, some students just remember these numbers down here, and that's it. Some students just remember these numbers down here. I think it's a better idea. But it depends, it's up to you. Now, what I would recommend is get little cards and test yourself with them. And put on one side one piece of information from here. So it could be neutral metals, for instance, and you've got to remember the other three. Or you could put this one down, and then you can remember these other ones here. But remember, the examiners will ask you in any order. So they'll give you, for instance, 14,000K. What's its spectral classification and what's its colour? Blue, B, and it's got helium and hydrogen in it. Go away, make some of these cards together, and then start memorising those. I can't help you with anything more than that. You just have to get it in your brain. Meanwhile, I'm going to go on and talk about something else. So go away, do that, and then come back. So we can do a bit of practice once you've got that there. So sum of triangle consists of 3 stars, Altair, Denham, and Vega. Some of the properties of the 3 stars are summarised below. Brilliant. There we are. Sum of triangle. If you watch my other lesson, you'll know what that is. So there we are. There's temperatures. Ooh, temperatures are quite close, aren't they? Look at those. Quite close range there. 3 stars belong to the same spectral class. State and explain which spectral class they belong to. So you have to absolutely know which one they are. Go to your brain cells. Deduce which of these stars appears brightest. So appears brightest. Appears brightest. Apparent magnitude. So apparent magnitude, which one of these is the brightest number? Hipparchus, remember, he just didn't do it very sensibly. So of course, work that one out. And then calculate the distance from it to the closest of these 3 stars. Which of these is the closest? You can do that brute force by using n minus m, 5d log 10, or you can work out which one of these is closest. So which one of these is the most negative when you take away little m from big M, which is apparent magnitude or magnitude. So pause this, try and work those out, and then I'll show you the answers. And there are the answers. Spectral class A, because it was 7,500 to 11,000. Lowest value is Vega. And then, of course, Altair, because n minus m is the most negative, which was minus 1.44. And then, of course, you put the numbers in, and then you get 5.2 parsecs, which is pretty close, really close for a star. Well done. So, Hertzsprung-Russell diagram. Don't draw this. This is a very detailed one. I just want to get you the idea of what the Hertzsprung-Russell diagram is in colour. So Hertzsprung-Russell diagram is a diagram which up the y-axis is luminosity, absolute magnitude, against temperature or spectral type, but it's going backwards. So in other words, the temperature is the highest towards the origin and lowest towards the not origin, from the other way. And you can see it's logarithmic scale. Both are logarithmic scales, which means in luminosity units on here, you go from 10 to the minus 5 up to 10 to the 6. So you can see the range of stellar luminosities is quite large. And you can see that O, B, A, F, G, K, and M really do this. Now, this is not the way AQA want you to remember it, but it's a really good way. We've got areas. We've got white dwarfs. We've got the main sequence, which I'll talk about more in a second. We've got giants, and then up to the top, you've got supergiants. And you can already see some of our popular ones that we've already heard of. Sirius, Vega, right there in the middle. Sirius, Vega, right there in the middle. We've got Deneb, Rigel, stars in Orion. Then you've got Betelgeuse, the other star in Orion as well. Polaris, the North Star. Aldebaran, Arcturus, Pollux, part of Gemini. All of these stars on here, some of you have probably not heard of here, mainly because these stars are the reddest stars in the sky. And then you go right up to Bellatrix, Spica, which is a star that you'll only see in the very, very southern sky from Britain. So this is, now, AQA don't want you. This is AQA's version. Now, so a student once nicknamed this the sausage diagram, and you can see why, because there's three distinct sausages. You've got a very long, bendy sausage. You've got a very sort of chipolato-like one in the bottom left-hand corner, where the dwarfs are, and then you've got a standard sausage up here, which is the giant sausage. Remember, if you like that way, I don't mind. But what about this diagram? You have to draw this now, and you're going to draw it over and over again. So, do the axes. Notice the axes are crazy. 15 at the bottom, minus 10 at the top, because that's increasing absolute magnitude. And then O be a fine girl, kiss me. Notice this is linear on here, so it's just all separated. O be a fine girl, kiss me. Only boys, excepting feminism, get kissed meaningfully along there as well. And therefore, you've got the giants at the top here. You've got the main sequence, which comes down from minus 10, flattens off around the sort of 2, 3-ish, and then goes down all the way down to N to 15. The dwarfs are no redder than A, which still means they're blue-white, but nevertheless, the dwarfs in this corner between the 10 and 15, and the giants occupy between minus 10 and 5 at the top there, from B all the way across to M. So therefore, you've got that. That's the one. Press pause, go and draw that about 4 or 5 times from memory. Look away from the screen, shut your laptop, whatever you do, and then get those down. You need to learn that off by memory, because the questions are draw that effectively. And this red line here is the stellar evolution path of a star, similar to the sun. So it pops out from the main sequence. Main sequence, by the way, is a sort of the middle age of stars. Stars hang around on here for a very long time. They get born, they come here, they burn, in inverted commas, fusing, for billions and billions of years. And then they come up here, they start to lose that fuel. I'll come on to stellar evolution in a bit. They stay a giant for a while, not very long, and then they either go bang or they blow off all their outer layers and go all the way down here, getting very dim but hotter. Notice? And effectively dwarfs are the cores of stars, the dead cores of stars, like a little cinder that's left over. And white dwarfs, which you'll have heard of, come down here and then turn into black dwarfs, which are cooler, basically. And they're cooler, they will go this way. But they'll essentially be still very hot stars. The centre of a star is pretty hot, and they stay hot for a long while. And because they're very small, they take a long while to radiate their heat. So pause the video, go and draw that 10 times-ish. Okay, I've given you some websites here. I know you can't click on this video, but really good to go and watch some of these ones here. And so we end up dwarfs. I think it's dwarfs with an F. But anyway, there you go. Internet rife with spelling mistakes. And you can see a slightly different look here. This is luminosity here in watts. And then you've got surface temperature here. So this is the sort of the central section of here. We haven't quite got the O's on here. And then the sun is here. This is where I did this, because this is where the stars are born. It's not on the AQA, but this is where they're born. And they go and then sit here for a long while. Then this is fast, super fast all the way down here. So fast, fast, sit on there for a billion years, slowly getting faster, 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 very fast, and done. Okay, right. So I promised this is what the questions look like. On the axis below, labeling the main sequence, giant stars, white dwarf. They've given you the spectral class, but they haven't given you the absolute magnitude. Remember, it's crazy. It is crazy. So get that magnitude right. Go back and watch the bit of the video that I want to check, and then do your sausages. Sausage, sausage, chipolata. Okay, so what are absorption lines? So if I take a spectrum of a star, so if I get a telescope and I work out what wavelengths are coming from it, I end up with, it's hidden behind it, that says wavelength and intensity. Remember, intensity is the power per square meter at the Earth. So if I'm measuring something from the Earth, I end up with these dips in my emission. So in other words, if I'm measuring wavelength between about 400 and about 700 nanometers, I end up with these dark lines. And they're very distinct, very narrow dark lines. And it didn't take us long to realize that these were due to gases on the atmosphere of stars. And that means not the gases that make up the star, but the gases that are just a little bit beneath. And this is what I tried to do here. So here's your sun, any sort of star, all the light coming off it. So this light here would be completely flat. You wouldn't have any dark lines on here. And then a gas in front of this star, this light gets absorbed, and then it radiates its light in all directions. But it only absorbs certain wavelengths depending on what the gas is. So this gas is hydrogen that's up in front of the star. So if you're all the way down the Earth looking this way, it'll only absorb certain wavelengths associated with certain electron energy levels in the atoms of hydrogen. In this case, these lines are called Balmer lines, and they're called Balmer lines because they start and finish at n equals 2. n equals 2 is the second energy level. So this gas is already quite warm. It's already quite warm anyway, so to get all the electrons up to n equals 2. Photons come in, they get absorbed, they go up, and then they spontaneously go back down again. And that gives out a photon. But it won't give out a photon in the same direction, it'll give it out in all directions. So this light coming in gets absorbed by a hydrogen atom, the electron around the hydrogen atom. The electron goes up, say to n equals 6, then drops directly back down again to n equals 6. And that gives you a wavelength of a large drop. Therefore, it's a high energy. Therefore, it's a short wavelength, high frequency. So this one is more likely to be this here. And I've lined these up so it fits quite nicely. So this one here will be a UV line at 410 nanometers. This one's going to be blue, and this is going to be less blue. And this one here is going to be a red line at 656. Why is it red line? Because this is the smallest energy leap, because that's the smallest amount of energy that's associated with long wavelength photons. And this is where it's tricky, because long wavelength photons have the smallest energy leaps in the outside of an atom, hydrogen atom in this case. And why do they appear darker? Because they're absorbed in this direction, and they're radiating in all different directions, which means that only a very small amount of light at that wavelength will continue to be emitted. So in other words, this is not completely dark, this is not a bottomless pit, but it's certainly a lot darker. And you can see that this one's deeper than this one here. So quite a lot going on there. Hydrogen and Balmer absorption lines. It's quite a tricky concept, and to be sort of relegated to a line underneath the table in the specification is worth spotting. Okay, so and this is it in more detail. So hotter continuous source, it's a star. This is what the spectrum looks like before it hits this cloud in the way. This is the cloud, just like I had in the last one. So photons come here, they pass through the gas. But when they pass through the gas, they're absorbed and they're emitted into different directions. And they all start at n equals 2, because that's what makes a Balmer line, n equals 2. And then they're all scattered in different directions. And you end up with a spectrum that looks quite bitty, looks like bits nibbled out of it. And these all refer to the different electron absorption spectral jumps. And this is the detail. Here the photons coming in. You've got an atom which then jumps to a higher level. Notice one of the photons has disappeared. We had 4 coming in. We've got 3 here now. That electron goes up to there. It's in a higher energy orbit. And then after a certain amount of time, it will drop down again. But this time the photon is emitted in this direction, which means it will be dark. In other words, that particular photon will be missing, and hence it will be one of these lines that's represented on here. And what's useful about this slide is it tells you about the E2 minus E1. In other words, the difference in potential energy between these two will give you the actual energy of the photon. And that energy equals HF, of course, from earlier on in the course, or equals hc over lambda, which will give you the wavelength, lambda being the wavelength. and therefore you can calculate the actual wavelength that's associated with it and where this should appear. Really nice piece of physics is hydrogen Balmer absorption lines, and it tells you a little bit about what's between us and the star. It won't tell you about the actual absorption going on in the centre, but it will tell you about this. Now, another aspect of this, why am I talking about this here, is because this appears stronger and weaker in different stars. So, for instance, in an O star, it's weak. Why is it weak? Because it's too blooming hot. In other words, instead of the electrons going to n equals 2, they go off straight away. Hydrogen's ionized. Can't do it. Too hot. B, it's slightly stronger, but it's still too hot. It's kind of the Papa Bear version. The porridge is too hot. In this case, the atmosphere. The star is too hot, and it ionizes the atmosphere. Now, A is the strongest. Just right. In other words, the high abundance of hydrogen in the H2 in n equals 2 state. F is weak, again, because it's too cool. They're not getting to the n equals 2. They're still in n equals 1. And then G, K, and M, there's hardly any, because there's not enough atomic hydrogen to be able to get to the n equals 2. They're all staying at ground state. So there you go. O weak, B slightly stronger, A is the strongest. A class at hydrogen Balmer lines. That's how some of my students have remembered it. It's A class at hydrogen Balmer lines. It's the peak of it, in the middle. And I think that's why the examiners pick Balmer lines, because it's nicely in the middle. Okay. So here's a typical question. So detailed analysis like from both of these stars here. So Bellatrix and Betelgeuse. To which spectral class do Bellatrix belong? So there you go. It's 22,000. It's not in the top, is it? Oh, B. Ah, right. It's B this. That's why you got to remember these things. Prominent features are Balmer absorption due to hydrogen. State another element responsible for. So that's why you've got to get that in. So look on your little card you've created to get that in there. Why does the spectrum of Bellatrix not contain prominent hydrogen Balmer absorption lines? So Betelgeuse here, you can see, is much, much cooler. Now you have to do the right reason why you don't get prominent hydrogen Balmer absorption lines, because it's much too cool, therefore electrons cannot, and it's giving you a 3-mark answer for that as well. So that's a really good question. You want that to come up if you've revised hydrogen Balmer lines, because I know a lot of students won't. And there it is, B, helium, and of course the temperature is too low to get to hydrogen in that state. I cannot tell you how important it is to just go away and remember these things. You have to remember this. So use key cards, use mind maps, use colour revision, repetition. You have to give one part of it. So in other words, make sure you do a resource where, so right, temperature is 6,500. Tell me everything about 6,500. It's white, it's an F star, it's got ionized metals in there as well, and you've just got to repeat it.